All right, hello everybody. Welcome to your lesson today on optics, specifically looking at plane mirrors and starting to look at curved mirrors. So prior to the start of this video, you should have received this handout for your note taker, and you should have started to complete this warm up where you draw and label the following object image with incident ray, reflected ray, normal, angle of incidence, and angle of reflection. So just to kind of show you what your image should look like at the end of completing this warm-up is you always draw the incident ray from the object to the mirror and then the reflected ray from the mirror to your eyeball. How you know where this point is on the mirror line is because your reflected ray is always going to be a straight line towards where the image is, the virtual image on the other side of the mirror. So once you kind of make this line drawn towards the mirror, you can then create your dotted virtual reflected ray all the way to the image here. And from there, you can draw the incident ray, which is going from the object to the mirror here. You also know that your normal is perpendicular to the surface of the mirror. And you know that your angle of incidence is from the incident ray to the normal. And your angle of reflection is from the reflected ray to the normal. I've also asked you to add to your drawing P and Q. We're going to go over these terms here in a moment of these different distances, but while I have this image up, why don't you go ahead and label this? There is a distance from where the object is to the mirror that we call distance P. And then the distance from the mirror to the image is what we call distance Q. So go ahead and take a moment and add that to your notes and kind of make any corrections that you need to on your note taker for today. All right, so pulling up the rest of our notes for today. First, we're going to begin by looking at the rules of a plane flat mirror. We've talked about flat mirrors a lot. We started a lab in class yesterday, but here's some very specific things about it. What you should have learned from your plane mirrors lab is that the angle of incidence is always equal to the angle of reflection. So you should see very common values between the normal to each of those rays that you're going to draw. A new vocabulary word that you've heard us use in class thus far is what is a virtual image. This is the image that is created behind the mirror. It's not actually there. The object of the pencil is not actually behind the mirror, but it is the image where the light appears to be located. Now, we know that light reflects off of a surface back to our eyes where we're taking in that light, but our eyes kind of treat that light like it could just continue to move in a straight line and actually be reflected off the virtual image that is virtual. It's not real, but it appears to us to be located behind the mirror. Some other important rules about plane mirrors that you kind of learned in your introductory video is that there is left to right reversal of images. That one you don't have to write down as much, but what I do care about that you have written down is that this kind of new terms that we just labeled on our warm-up drawing, which is what is P and what is Q. The object distance from the mirror is what we call P. So the distance from the object to the mirror. What we call Q is the distance from the image to the mirror. There is a mathematical value that determines that P as a distance is always equal to Q's distance. Whereas in a plane flat mirror, when we talk about the size of an object, the size of the image appears to be the same size of the object. So this allows us to do a little bit of calculations with magnification once we start to get to concave and convex mirrors. But in plane mirrors, we just assume those sizes, the magnification would just be 1. We can't get anything any bigger or smaller when a plane flat mirror is in use. So you kind of see all of those values labeled on this pencil example right here. The height of the pencil and the object is the same as the height of the pencil in the image. P, distance from the pencil to the mirror, is equal to the Q, distance from the mirror back over to the image. And the angle of incidence and the angle of reflection are also equal in terms of our measurements there. So now what we're going to start to look at this week and investigate in the real world are curved mirrors. There are two types of curved mirrors. One is concave and one is convex. We're going to start by looking at curved mirrors in general, their focal points, or excuse me, their like vocabulary terms to talk about different types of mirrors, but today specifically is going to be focused on talking about a concave mirror. So you're going to see this diagram that you see here a lot today. We're going to learn how to draw one. Some just terms that you should be really familiar with at this point in time are object, image, incident ray, reflected ray, and normal. But let's add a few more vocabulary words to our list that you're going to fill in the table on your note taker. The first of those vocabulary words is called a focal point. When a mirror is curved, it directs all of the rays of light to one position where all of the rays of light come together. If you've ever seen like a bathroom mirror that is concave, it's curved in towards your face, there's a place where we can actually focus all of those light rays into one section. This will also kind of relate to lenses as well. If you think about a magnifying glass, like burning ants on a sidewalk, because of the curvature of the lens, you're allowed to direct and bend all of the light rays to one position. On this image here called a ray diagram, you can see the focal point from this concave mirror where all of the light rays will be directed. Where we can kind of differentiate the discussion of focal points is using terms like real and virtual. A real focal point is going to be on the same side of the mirror as where the object is. It's real because there's actually light on that side of the mirror. So this diagram has an example of a real focal point where the focal point and the object are on the same side. We can then measure the length of where the focal point is as the distance from the mirror to where the focal point is being measured. If that distance is positive, it's being described as being in front of the mirror on the same side of the object. If that distance is negative, then that distance is behind the mirror where there is no light. But a focal point can still be back there for our different curved mirrors. So we've been using these terms a little bit in class, but let's give them an official definition. We've been using the terms real and virtual. A real image, remember, image is the reflection of the object you're seeing. So a real image that's formed is going to be on the same side of the mirror as the object. It's real. This is where the light actually is. So that is indicated as being on the same side as where the object is placed. This example picture right here has an example of a real image that is being located on the same side as the object. A virtual image, like we see with all of our plane mirrors, is when the image forms behind the mirror. There's not actually light back there. That's why we call it virtual. But your brain can't determine and process that light is actually being bended to create an image where there is no actual light. So we instead actually visualize that there is something back here behind the mirror, even though we know for certain that there isn't. So we call this a virtual image because it's like fake in nature. It's non-existent, but it is what our brain is kind of deceiving us to actually see. So there are all of your terms there. We're going to use them kind of moving forward as we talk today about a concave mirror. So you should be able to flip the page. First, we're going to talk through a little bit of mathematics, and then we will discuss how to draw ray diagrams. So a concave mirror is a mirror that if you were looking in a mirror, it would be curved towards you. We're going to identify today a mirror equation that has to do with some of the variables that we just discussed. So this mirror equation uses the three variables of the object distance, which is P, the image distance, which is Q, and the focal length, which is F. This concave mirror equation states that 1 over P plus 1 over Q equals 1 over F. So make sure you have this equation written down and you have kind of what is P, Q, and F written down on your note taker. As you can imagine, when we're talking about distances, obviously the standard unit for a distance is a meter, but more likely than not, when you are working through sample problems, you're going to be using centimeters because we can't see images that are meters away from a mirror. We only really see images that are centimeters away from a mirror. So it's okay to use that as your standard unit when you're talking about your P's, your Q's, your H's, and your F's. Lots of letters in this one. So we have this ratio relationship between P, Q, and F where they are all related by these fractions. We're also able to measure what is called magnification. What is the size of the image as related to the size of the object? Curved mirrors allow us to either magnify large or magnify small the images that we see. So we're relating image height or the distance to object height or distance respectively. So this equation, the capital M stands for magnification. This is just a value that doesn't have a unit. It's just going to be greater than 1 or less than 1 in that sense. Less than 1 if the image is getting smaller. Greater than 1, the image is being magnified to be larger. It is equivalent to kind of two of the same types of equivalencies. You could either describe this in terms of image height versus object height, which would be primes on, that's the kind of apostrophe there that you see on this H, indicates that we're talking about the image. So image height would be H prime divided by H, which is the object height. So if it has that apostrophe, we're talking about the image, not the object. This same equation would also relate to the distances between the image and the object. So remember, image distance is represented by Q, object distance is represented by P. This is a negative value when you are using image distance, but it is not negative when you are using your heights. This is negative because your image distance, because this will kind of help with it being virtual or real. Remember, if it's behind the mirror, the image is behind the mirror, we indicate the image to be negative, hence why that negative value is there. Okay, so we'll use these equations here in a moment. For now, we're going to introduce how do you draw a diagram that accurately can measure the distance of all of these focal points and lengths in a mirror. So what can a ray diagram be used to do? It can be used to locate an image, identify if the image is real or virtual, reveal if the image is right side up or upside down. So this is an example of a ray diagram. Usually includes at least 2 rays to locate where an image is, where those rays intersect with one another. There's some generic rules that I've kind of written on your sheet right here, where you're kind of going to just follow this pattern for all of the rays that you draw. The first ray that you draw is always going to be in from the object parallel to the mirror and then out through the focal point. The second ray that you draw is then going backwards in through the focal point and then back out through parallel. These rules, you'll hear them over and over again, and they'll make a little bit more sense once you get to do some practice on your own. So I have these rules posted up here. Let's kind of first just look at an example visually before we start drawing them ourselves of what does it look like if your object is outside of the focal length. So here you are the kind of lines that you're drawing. Now on this diagram, the one thing I don't like is that they've drawn the mirror as actually being curved. You are going to draw them as a straight line, and you're just going to label it concave mirror because that makes it so that the lines that you're drawing parallel aren't getting curved or tilted as well. So here is our object. Your object is always represented by an arrow. If you're drawing an object, if it's a cat, you're not going to actually draw a cat. You're just going to draw an arrow here and label it O for object. Your first ray is this line right here, coming in from the object parallel until it hits the mirror and is reflected back off, and it moves through the focal point. That's rule number one. Again, in parallel, bounces off the mirror, out through the focal point. The second rule for a second ray that you would draw would be in from the object, again, always starting from the object, in through the focal point, bouncing off the mirror, out parallel. Again, in through the focal point, out parallel. Where the two lines intersect is where your image will be. You will then draw this as an arrow. This time you can kind of actually see the magnification from this concave mirror made the image smaller. And it is also inverted, which means it is upside down. Let's look at an object that is inside of where the focal length is, using both of these rules here. So here in this case is our object. Again, we're going to actually draw our mirror lines being straight. And so the same rules apply, but we're starting to create a virtual image. So some of our lines have to go backwards out from the where the mirror is into the virtual world. So our first line, when the object is inside the focal length, went in from the object to parallel, and then out through the focal point. So these black straight lines, again, in through parallel, out through the focal point. The second line went in through the focal point, so I connected my ruler from the focal point to the tip of the arrow, connected it in towards the mirror, and then out parallel. You'll notice that this arrow and this arrow are never going to intersect. So that means that the image is not ever going to be real on this side of the mirror. If we extend both of these lines, though, out into the virtual world, we can see where the image is created in the virtual world, and it's upright and it's magnified to be even larger. So I'll bring out a real concave mirror in class next week so you can kind of experience walking in towards a mirror and out away from it and seeing your image be flipped, being magnified greater and smaller depending on if you are inside or outside of the focal point. But I appreciate you kind of imagining along with these diagrams as we work through today. So we are going to go through a couple examples here on our own. Let me just stop sharing my screen here. Okay, great. So you should have a straight edge ruler or protractor. If you do not have one already, you're going to need one. So this says draw a ray diagram for a concave mirror with a focal length of 4 centimeters and an object 6.5 centimeters from the mirror. Your object is 1 centimeter tall. So I'm going to start just by drawing my mirror. Remember, we're going to draw it as a straight line using our straight edge, and we're going to label this mirror MM. And I'm also going to just kind of write up here, oh, this one's concave. Then we're going to just create perpendicular to where our mirror line is. So I might kind of plop right here. Here is 90. Make sure I have a nice straight perpendicular line, because this is where, like if we were putting the mirror up on an edge, where I would draw kind of where the surface is at. I ended up a little wonky, but as long as this is perpendicular, we're all good. So we got to actually measure and draw these different points on our diagram. So let's start with the focal length being 4 centimeters. We're actually going to measure 4 centimeters from where our mirror is. 1, 2, 3, 4. Place a dot. And your focal length is always drawn and represented by this like curly QF. The next thing we label is the object, which is 6.5 centimeters from the mirror. So I come over 1.5 centimeters. And remember, your object is represented by a P, always keeping your labels on there. And lastly, your object is 1 centimeter tall. An object is always drawn with an arrow. So I'm going to make an arrow that is a line that's 1 centimeter in height that has its arrow pointing upwards. So to draw the ray diagram, we're going to follow our 2 rules. In parallel, out through focal point, and then in through focal point, out through parallel. So this is where the parallel part, you're going to do your best to be parallel with this other line that you've drawn. I really just ask like for your best kind of eyeball of a parallel line to be as accurate as possible. The straight edge of the ruler can also really be helpful with this. So our very first line, starting at the object, goes in parallel until you hit the surface of the mirror. From the object in through parallel until you hit the surface of the mirror. Your next line, from the point where you intersected of the mirror, goes in through the focal point. Except for, I forgot the second part of this. Excuse me, in through parallel, and then now you're going, the second part of rule number 1 is out through the focal point, is what I was trying to say. And I draw a little arrow at the end of this to indicate what direction it is going. So we went in through parallel, out through the focal point. Now we're on to our second rule. Our second rule, again, starting from the tip of the arrow, always starting at the object, this one goes in through the focal point. So I line up my ruler at the top of the object through where my focal point is located. And we go in through focal point until we hit the surface of the mirror. And then we go out parallel, doing your best to create a parallel edge. Now you notice where I originally drew my first line, I didn't draw it long enough to intersect. So I might just have to extend this. That's why we're always working with a pencil with these diagrams, no problem at all. I have the 2 direction in which these arrows are headed. And now where these 2 lines intersect is my image. So I'm going to draw a straight vertical line from my surface down to the intersection. Because this is below our surface, my image is now upside down. We call this being an image that is real and inverted. All right, that is example numero 1. All right, let's go over example problem number 2. This says draw a ray diagram for a concave mirror with a focal length of 4 centimeters and an object 2 centimeters from the mirror. And again, the object is 1 centimeter tall. So to start out, you're going to set yourself up with your mirror, which is just a straight line, regardless of the fact that this is a concave mirror, which is a curved mirror. We're always going to draw our mirror with a straight line, and we're going to label it MM. You're also going to create a perpendicular surface to the mirror that's just a straight line coming out at 90 degrees to make sure that you have like a reference point for what is parallel to that surface and the surface in which the object is resting on. And that surface can go on both sides of the mirrors. So I kind of have like my standard setup right here. All right, so let's start to draw the locations of our focal length and our object. So again, actually just measuring with your ruler, we have a focal length of 4 centimeters. So I'm measuring from my mirror right here, 4 centimeters. And I'm going to label that focal length with that nice little curly Q F. Then we have the object, which is 2 centimeters from the mirror. So notice that this is different from the last example that we went over because now the object is inside of the focal length. So here's the placement of where that object is. Remember, the object location is labeled with P. And we're going to draw the object as an arrow that is 1 centimeter tall, as it says in the instructions. So I draw a line that's 1 centimeter. Put a nice little arrowhead on it, and there we have our object. Okay, so now we are going to use our same exact rules. The very first rule is that you go in parallel to the mirror, out through the focal point when you're drawing your different ray diagrams. So we'll start from the top of the object. Remember, you're just doing your best to eyeball what parallel is, and you're going to draw a straight line in towards the mirror, in that straight line until it hits the mirror. And then you're going to draw from this point where it bounces on the mirror out back through the focal point. So I line up from this point here to my focal point and draw out this way. My second rule for drawing a ray diagram is my second kind of set of lines go in through the focal point and out through parallel. So this one's funny because if you set up from the top of the object to the focal point, you actually have to angle this so that the line that you're drawing is still from the top of the object to where the mirror is, but you're aligning it as this line would be across from the focal point to the top. But you only really need to draw the line from the object to the mirror as such, like that. So I went from the top of my object to my mirror, and when I release my ruler, that's the first part. That's in through focal point. Second one says out through parallel. So this is where I'm using kind of my best eyeball devices. From where this point hit the mirror, I'm drawing a line that is moving out parallel and away from the mirror. So we always say where these two kind of out lines intersect is where our image is going to be. But if you notice, these two rays are going away from each other. They're diverging. They're never going to intersect, which means that this image will never be located in the real portion of the mirror, on the side of the mirror where the object is. So that means that we actually have to look at these lines in the virtual side of the mirror, on the back side. In order to do that, we can actually extend these reflected rays out and backwards towards the virtual world. So let's start with our first one that we had here. This one went in through parallel, out through the focal point. I can extend the out through the focal point part. When we go in the virtual world, we're going to draw these lines with dotted lines to indicate that we're talking about in virtual. And I can do the same thing for my in through focal point, out through parallel line, extending from the place where there is parallel. Again, a dotted line to indicate that we're in the virtual side of things. And now you see there's a clear place where both of our virtual lines intersect. And that is where our object is. So we draw an arrow for our object from our surface upwards, indicating it as an arrow again. And for this one, we see that our image is amplified and it's greater in magnification. But our image, this time instead of being real, is virtual. And it's also upright. So those are nice things to recognize about the difference between these two example problems is that when you had your object outside of your focal point, you ended up with an image that was real and inverted. When you had an object inside of a focal point, you end up with an image that is virtual and upright. And that is a pattern that you will continue to see as you draw these ray diagrams. So we're going to try one more all together, but this time we're going to pause the video and I'm going to give you a chance to practice this on your own. There's sample problem number 3 right here. It says a concave spherical mirror has a focal length of 10 centimeters. Locate the image of a pencil that is placed upright 30 centimeters away from the mirror. Find the magnification of the image and draw a ray diagram to confirm your answer. So this is putting together everything that we've learned in this lesson video. Not only are you going to be drawing a ray diagram as we saw in these past 2 examples, you're also going to be using the equations that we use at the top of this page for the equation, the mirror equation, and the equation for magnification to answer things like finding the magnification of the image. So you're going to do this on your own piece of paper. One last hint before I kind of give you some time to do this. Notice that the distances are 10 centimeters and 30 centimeters. You're not going to be able to fit that onto one piece of paper. So you're going to have to create a scale. You're going to have to create a scale for every 10 centimeters is so long. I suggest doing every 10 centimeters on your scale being 1 centimeter on your ray diagram. And I also suggest drawing drawing an object that is 1 centimeter tall, as we have been doing. I don't know if it explicitly says that here, but again, you're going to need a scale. I suggest 10 centimeters equals 1 centimeter, and that your object, again, is 1 centimeter tall. That'll just kind of help you draw your right image and using your mirror equation and your magnification equation. So at this point in time, will you please pause the video and we'll come back in approximately 10 to 15 minutes when everyone has had a chance to do this. You can press play and see the answer. All right, welcome back. So my assumption is that you have worked through problem number 3 on your own, and I'm just going to kind of go through kind of your solution of what you should have just done. So part 1 of this problem is to determine the size and magnitude of the focal length and the object size. Because we are given the focal length, we're given the location of the image, but what we really want to know is where kind of our object is going to be placed, and as well as our image. So really what we're given here is F, and we're given P. Now something I want you to note is that this was noted in your notes, but just as a reminder, P is positive if it's in front of the mirror, and it's negative if any of these values are behind the mirror. So for concave mirrors, your focal point is always going to be positive as well. From there, once we've kind of indicated our known values from the problem, you're going to use the mirror equation to relate the object and image distances to the focal length. So we're given this equation that 1 over P plus 1 over Q equals 1 over F. You can rearrange that to solve for Q, where you get 1 over Q equals 1 over F minus 1 over P. So we plug all of that into each other. Remember, we're looking for our whole value. And we get Q is equivalent to 15 centimeters, which is going to help us with the drawing of our picture and also to answer the question of what is the magnification that we are looking at. So remember, magnification is a value that is a ratio between your image distance and your object distance. So magnification equals negative Q divided by P. You plug in your values here, you should have gotten that your magnification is negative 0.5. So this negative to you should be indicating that when you draw your ray diagram, the image should be smaller. That's also from the 0.5 here as well. And the negative is telling you that it is inverted. It is upside down. So lastly, you should draw your ray diagram using your rules. So this is kind of the full final product here. Again, we used a scale of 10 centimeters to every 1 centimeter, and our object is 1 centimeter tall. So with that scale in mind, we drew our 1 centimeter object 3 centimeters away from the mirror because it originally said 30. And then we drew our focal point about 1 centimeter away from the mirror because it was originally 10. Our first rays went in through parallel, out through the focal point. So again, from the object, in through parallel, out through focal point. Our second set of rays went in through the focal point and then out through parallel. The place where these two rays intersect with one another is where our image is. If you measure it, you should actually see that it's 0.5 centimeters tall, which matches our magnification value, and it's also upside down and inverted, which matches the value of the fact that magnification was negative. So our final conclusion is that the image is real and inverted. All right, so that's a lot of new information for today. You have one more opportunity for practice today, which is your homework assignment. It is just one problem. It is on page 462, number 2. This is again going to be a problem where you have to use a scale in order to be successful. Once you do that, we'll have time to go over and practice that all together on Tuesday. If you have concerns about doing it along the way, there's also a key on Schoology that you can check to look for accuracy. Once you are done with your homework problem, you also have the opportunity today to finish up any aspects of your plane mirror lab that you need to do because that is also due on Tuesday. Good luck with the rest of class. Materials should all be available to you, and I am available during advisory today. I will be around in school, so please come by if you have any questions or send me an email, and I look forward to hearing from you. All right, thanks, guys.